In fact, why don't we just let's do this. We'll work over here so we can pop back and forth. Same problem, only let's change some numbers. Let's say that our 20-foot ladder is, what do we want to say? Let's say that it's 15 feet up the wall. All right, so same sort of deal. I want to know the angle that it makes. Let's call this beta so that we're nice and comfortable. I want to know the angle that it makes with the horizontal down here. Or I could be fancy and tricky and say, ooh, I want the angle that it makes there. There are lots of ways that we could do this. I could call this alpha. All right. Now, hopefully, most of you were saying that Ripley, since this is a right angle, right, which I know I didn't throw that in there, but I am now. Once I have beta, I have alpha because I can just subtract it from 90. Or I can do it with another trig ratio. Let's do it both ways. All right, I'm going to solve for beta first. Now, think about this. Again, opposite, we want to orient ourselves. This is opposite. This is hypotenuse. This is adjacent, right? I'm trying to solve for this angle that it makes. So I know opposite and I know hypotenuse and I want beta. That's the coolest thing about right triangle trigonometry. There's always 3 variables and you pretty much need to know 2 of them to be able to proceed, or you need to know 2 equations with 2 unknowns, right? Or 3 equations with all 3 unknowns, but that's for linear algebra. All right, so what trig ratio deals with opposite and hypotenuse? Sine, right? So, ka, to, a. So, I sound ridiculous. All right, so the sine of beta is equal to 15/20, right? So beta is equal to the inverse sine of 3/4. Now, remember, as soon as I see that, let's change colors here. As soon as I see this, I need to remember that the range of inverse sine is from negative pi halves to pi halves, right? That's really, really key, which in this case is great because I know that beta, in the context of the problem, I know that beta is going to be between 0 and 90 degrees, so between 0 and pi halves. So we're okay. We're not going to panic here. However, if we're in a situation where we know that we're going to end up with an obtuse angle, an angle greater than 90 degrees, then I have to do my dance and be real careful. Remember that? If I do my inverse sine where I move it around to get to the value that I need it to be at. All right, so let's stumble over here to my calculator, and we're going to go inverse sine of 3/4, and voila, remember I'm in degrees. Sweet. So it appears that beta is approximately, because I'm rounding here, 48.59 degrees. Now it's easy to get alpha, right? Alpha is a freebie. I know that alpha is equal to 180 degrees minus 180, try that again, 90 degrees, right? Because all of the angles in a triangle sum to 180. Hopefully you remember that from your geometry days. And this thing's already gobbling up 90 degrees because it's a right angle. So let's see, what am I doing? 90 degrees minus 48.59 degrees. Let's see if I can do that in my head. What is that? 41.51, right? 41 degrees. Okay? Easy peasy. If I need to check, I can always add this to this, and sure enough, I get 90 degrees. Sweet. Now, whoa, but let's say that I didn't want to do that. Maybe I don't trust my subtraction ability on a test or on a quiz, and I want to solve for alpha another way. Well, okay, now this is where it gets tricky. This is where you have to orient yourself per alpha. This is no longer opposite. It's adjacent. This is still the hypotenuse, which is good. This is no longer adjacent. It's opposite. So remember, I still know what 15 and 20 are, right? They're known, and I want to be able to use an adjacent and a hypotenuse ratio to solve for alpha. Ka, let's see, adjacent hypotenuse, ka, ooh, that's cosine. So I know the cosine of alpha is equal to 15/20, right? So doesn't this imply that alpha is equal to the inverse cos of 15/20? Now again, my spidey sense needs to tingle a little bit, although not as much as it does with inverse sine, because I know that the range of inverse cosine is from 0 to pi. So I don't have to be as crazy with this one because, if you think about it in real world context, angles are always going to be between 0 and 180 because you can orient them geometrically however you like. You can draw an angle wherever you want. It's still the same angle. Okay, so I'll stumble over here. Again, this reduces to 3/4, of course. So I'm going to go second inverse cos of 3/4, and hopefully I get 41.41. Yay! All right, this is approximately equal to. Now again, well, in this case it works out nicely, but we want to round it. We want to get in the habit of rounding to thousands. 41.41 degrees. That's kind of cool, huh? Okay, let me show you one more, and then we'll be done. Because basically you'll have almost all of the skills. Let's say that. Let's keep it simple. Let's say I've got a cliff, and on top of that cliff, I got a tree. This one's kind of fun. Yeah, that's terribly drawn. Sorry. And I've got the ability to measure two angles, one from the base of the tree and one to the top of the tree. It's actually easy to make a little tool that does this. Okay, you can do it with like a paper towel roll and a compass, or excuse me, a protractor. I'll show you in class. All right, so let's say, just for giggles, that I know that the angle from the horizontal to the base of the tree. So this is called an angle of elevation, right? So think of an angle of elevation as if here's your eye. Whatever angle I have to raise above the horizontal, this is called the angle of elevation because I elevate, and this is called the angle of depression if I have to look down. This would be to depress, right? If I have to look down. So you'll hear those words come out, and you'll see them in word problems. Angle of elevation, angle of depression. All right, so just for giggles, let's say that I make an angle of, well, what's that look like? About 40? Let's go with 40. And then let's get a nice clean one here. Let's say that, so the angle of elevation from this point to the base of the tree is 40 degrees. And let's say that the angle of elevation from the horizontal to the tip of the tree, so this line of sight to the tip of the tree that looks kind of like 45 degrees, doesn't it? You buy that? Now, let's say also, just because, let's say that I know that the height of the cliff is, I don't want to get too crazy, but let's call it 100 feet. Okay? And I want the height of the tree. Now, let's see if we can figure this thing out. How am I going to be able to do this? There are lots and lots and lots of ways. You can do this kind of piecewise, one little chunk at a time. But if you really look at it, I mean, let's see what we can do here. I know this. I know I'm going to orient myself with respect to both of these angles. Okay? As far as this 45-degree angle is concerned, this is adjacent, right? Now, the 45-degree tells me that this whole side is opposite. Okay? That makes sense? So, if I want to solve for the height of the tree, what should I do here? What do you think? Well, there's a real simple way, and that is I can do, well, I got opposite, I got adjacent. Well, what do you guys think? The problem is that I have two variables, don't I? I'm going to need to solve for this adjacent side if I want to do this problem. Can you see why? If I simply write the sine of 45 degrees equals what? Well, it's going to be 100 plus h over, what is this? Call this z? I have two variables, right? I'm screwed. I can't solve for h. So that's not going to work. So, whoops. So what am I going to do? What should I do? Well, look at it closely. Do you agree that if I knew this, if I knew what this adjacent side was, my life sure would be pretty good, wouldn't it? Well, how can I do that? Well, I just do it in two parts. I know what, if I orient myself with respect to the 40 degrees, now let's change to that dark blue. I know that this distance, this 100 feet right here, this is my opposite. Notice for the 45 degrees, the opposite is the 100 plus h. But for this 40 degree, it's just 100. And I have adjacent. So I can actually solve for that. Now, wait a sec. Which trig ratio deals with opposite and adjacent? So, that's opposite and hypotenuse. Ka, that's adjacent and hypotenuse. Tola. People are walking by my classroom right now thinking I'm a madman. tangent. So the tangent of 40 degrees, let's call this x for lack of a better term. Okay? Tangent of 40 degrees equals opposite, 100, over adjacent, which is x. So x equals 100 divided by tan 40 degrees. Let's see what this is. I'm going to have to round a little bit on this, because I'll show you how you don't have to round to get a perfectly precise value, but I'll do that in class because we're close enough for government work. Let's put it that way. I'm going to stumble back over to my calculator. Excuse me, I have a hair in my mouth. I'm going to go 100 divided by tan of 40. Right? Easy peasy. And that gives me approximately 119.175. All right. Now look at what I can do. This is nice. Now let's change colors. Let's go back to black. All right. Now we're dealing with this 100 feet plus h. Now I know that again opposite. I know what the adjacent side is. It's 119.175. Right. So I know that the tangent of 45 degrees, which happens to be 1, right? Remember that? Is equal to what? 100 plus h divided by just opposite over adjacent, right? Which is 119.175. Now, hopefully you remember, we do this in our head without using our calculator, but we will check it with our calculator. All right, tangent of 45 is 1 equals 100 plus h over 119.175. See if you can do this algebra in your head. If I cross multiply, I get 119.175, and then I'm going to subtract 100. So doesn't h have to be 19.175 feet? That's how tall my tree has to be, 19.175. True? Let me think about it. Now watch. If I could stumble over here, and I go tangent of 45, which we know is 1, and then I multiply that, so times 119.175. It gets ridiculous at this thing, right? Now remember, we're gonna subtract 100 because I got to get h by itself, minus a hundo, and show enough. Oh, isn't that cool? That's fun, isn't it? So don't always think of right triangle trigonometry problems as being just one-step problems. They aren't. Sometimes they're 1 or 2 steps. Sometimes you're going to have to incorporate a whole bunch of ratios in at once. And that's the fun of it. These really are a good time. So hope you enjoyed it. I'll see you in class tomorrow. We're going to do a bunch of these. Have a great day.